Hi, this is my presentation at the Coloquium Chemometricum Mediterraneum of 2025, and this is joint work with Thorfinn Madsen, Carmen González, Caridad Díaz, and Pedro Sánchez Rovira. I will be talking about multivariate repeated measures designs, and I will start by providing a brief motivation of why we think this is important. These type of designs are commonplace in precision medicine, also in ecology. The type of design is in which we have several groups of individuals, maybe a treatment and a control group. The individuals only belong to one of these groups. The selection of this group is potentially randomized or not, depending on the design. And we also take several measurements for each of the individual, which is the most effective way of reducing the variance of the individual in the analysis. So examples of this type of design can be found in the precision medicine when we want to investigate the diagnosis or the effectiveness of the treatment in a given disease. Also in ecology, if we want to understand differences across groups of individuals. And in the example that I'm showing in ecology, for instance, rather than repeated measures in time, which is the most common case, we repeated measure in terms of the part of the body where we took the tissue. So it depends very much on the situation, but essentially these two type of designs will be analyzed in the same way. This is a Hasse diagram of the design. Basically, we have two main factors. The factor of the grouping, we could call treatment factor, and the factor for the repeated measurements, which could be, for instance, time. And both of them are related in a cross way. So basically, we have all the combination of the levels of A and B. And then we also have an individual, which is a random factor, and we identify it as a random factor because our inference is meant for the population of individuals, not only for the set of individuals that we have specifically in the experiment. And also the individual is nested in A because each individual is going to belong to a single group in A. And then we may have also the interaction. So we are going to use ASCA, ANOVA simultaneous component analysis, because it's especially tailored to this type of data coming from an experimental design. ASCA, as the typical univariate ANOVA, is based on three steps, which the first one is factorization. So basically, we break down the data in X into submatrices corresponding to the effects of the different terms in the experimental design, the factors and interactions. Then we move into the inference in order to determine which of these effects are significant. And for those that are, then we move into the interpretation, which is basically based on PCA plots. And why we think it is important to study this case is because we found this specific case study for response to treatment in colorectal cancer. And we found also that depending on the ASCA version that we will use, the response in terms of inference was quite different. We were mainly interested in understanding the difference of those patients that would respond to treatment in front of those that wouldn't. And depending on the ASCA version that we use, the results in terms of inference completely differ. So we wanted to understand why this was happening. And the reason why this was happening is that actually in the ASCA pipeline there are many decisions to make, and some of the decisions will lead to wrong results. So in this specific talk, I wanted to address the following questions about this type of repeated measurements repeated measures, sorry. And these are the following. What is the best way to code for nested factors in the design? How we should model random factors as well, because there are different extensions of ASCA that are could be applied to this case, and how the final model is gonna be affected by the specific distributions that we may find in the data, especially those that deviate a lot from the normal distribution, and by unbalanced designs. So let's move into discussing a little bit how the nested and random individual factor will be modeled in the first step of ASCA, the factorization. So here we have an example, which is an example of our type of design. We have a first grouping factor, children, adults, elderly, a second factor of repeated measures, time 1, time 2, and a third factor that is nested in the grouping. So an individual can only belong to one of the groups, can only be children, adult, or elderly. Now the way to code all this is, as you can see here, we have this part here correspond to the first factor, and the number of columns is exactly the number of groups minus 1, because the last group is going to be coded with minus 1s in all the columns. Sorry, this is called zoom coding. Then the second factor is going to be coded in the same way. Then we get the interaction, which is obtained from the column-wise multiplication of the main factors. And this coding here is for the nested factors. And you can see that the way of coding it is slightly different, because it depends not only on the set of individuals, but also on how, or on the groups that they belong to, right? So for instance, individual 1 and individual 2 belong to the group children, and they have a separated column for this group here. So the way of coding nested factors is slightly different. Now, as I mentioned before, we can use two different factorizations. The first one is based on the general linear model, and the ASCA version that uses this factorization is called ASCA+. So basically, our input is the matrix of data, but also the coding, as I mentioned before, for the different terms of the experimental design. And then we need to solve for the parameters of the model. So the parameters we need to solve are the averages and the different coefficients in the matrix B. We do this by minimizing this Frobenius norm and the sum of squares essentially, and we apply least squares to solve it so that we obtain the coefficients. And once we have the coefficients, we can put them into this equation, and finally we get the factorization. So x is factorized into the average part and the effects of the different terms and the residuals. Now, an alternative factorization is based on the linear mixed models, which is kind of the standard way in statistics to model this kind of designs in which you combine fixed and random factors. The extension for ASCA is called, or the most famous extension is called LMPCA, and is based on the estimation on a separate basis of the random components and the fixed components. And a particularity is that the authors start with a PCA decomposition of the data and then apply the LLM modeling for each of the components on a separate basis. Then at the end of the day, you obtain a factorization of x, which can be similar to the other factorization. And actually, it should be equal if the authors didn't make this or didn't need this PCA factorization initially, and the design was completely balanced. So we will arrive to exactly the same factorization in that case. A particularity of this factorization is that it's much more computationally heavy than the ASCA+. Okay, and finally, let's move to the, before we go into the results, let's move about to discuss a little bit ASCA inference. So the standard approach to compute inference is permutation testing. Basically, what we do is we extract the sum of squares of each of the parts in the design, and we do permutation testing to see if each of them is significant. But the statistic we can use actually depends on the design, the optimal statistic, at least in terms of theory. Okay, so basically in ASCA, typical software packages will use the sum of squares, which is the original proposal in the ASCA paper. But you can alternatively use F-ratios, which is kind of the most standard approach in the analysis of variance. The F-ratios depend also on the design. So basically you do the F-ratios from mean sum of squares, so you normalize the sum of squares by the degrees of freedom, and then the denominator need to be chosen wisely. So most often for fixed factors, this is the suitable F-ratio. But when we're talking about random factors, then in the design, then things change. And in our case, the optimal ratio is this one. And let me show you this from the theory of the expected mean sum of squares of the different terms. So these are the equations if we consider all the factors completely fixed. And in this case, the mean sum of squares of A is going to have a part that corresponds to the residual and a part for the factor itself. This is the part that we really want to check for inference, for significance, and therefore it makes sense to divide this term by the part that you want to get rid of. So basically F is going to start approximately at 1, and if it grows a lot, that means that this variance here is significant. But when we consider a random individual, now the expression of the mean sum of squares of A changes, and now the reference that makes more sense is the individual factor itself. So this is the correct ratio in this case, according to the theory, of course. So actually, in the case that I mentioned before, when we found differential results, it was because we weren't using the correct F ratio at the beginning. And then what happens is that the individual variability is incorporated into the variability of A, inflated, and then when we see this F ratio, we may think that we have a significant result while we haven't. And this also happens even if you use permutation testing. So actually choosing the most relevant F ratio is quite important. So let me end up with our simulation results. In this case, everything that I have presented so far is based on the theory of the univariate analysis of variance. So these are extensions to the multivariate world, thinking on the theory that is already well established in the univariate case. But the problem is that sometimes when we extend to the multivariate realm, things are not quite as we expected. So we wanted to check if all these considerations that I had made so far work properly in the multivariate world by doing simulations. And these simulations are based on power curves, which is an instrument that we have been using for the last 3-4 years, and that we have found to be quite meaningful for interpretation and for the selection of the correct version of ASCA in each case. So power curves work as follows. Basically, we generate synthetic data for a specific sample size. For a specific fx size. It could also be sample size, but for this presentation we use the fx size. And what we do is that we grow in intervals. We start from a variance of 0 for all the terms except for the residuals, and then we start growing all the terms and maintain the residuals at the same level. So basically what we are doing is iteratively creating more and more effect size into the simulated data. We do this hundreds of times for different effect size, and for each of these datasets we compute the ASCA model and we obtain the p-values, and we compute or we count the number of times that those p-values are significant. So basically they are below the significant level, which we fix at some point, for instance 0.05. So at the beginning, when the effect size is 0, we expect that all our ASCA results will show a p-value that is insignificant. Well, maybe not all, because we expect that the number of positive identifications, so basically all the p-values below 0.05, is going to be exactly 0.05. So if the percentage of time is at 5%, this meets the expectation of the significant level. So the power curve should start at the significant level. Then as we grow the effect size, we expect that more and more of the results of ASCA are going to be significant. And at the end, when the effect size is large enough, we should see that all the data that we simulate is significant itself. Now, when we have several ASCA versions, the optimal one is going to look like the green curve, starting at the significant level, as I said before, and growing up quickly. We don't like those curves that look like the red one because they will be overly optimistic. They will present a high type 1 error, and this is something that we don't want to have in real data because we are going to determine significance when there is none. And we will rather prefer the green one to the orange one because this one is growing slower, meaning that it has a higher type 2 error. So basically, when there is significance in the data, we wouldn't detect it as well as the optimal test. So this approach of creating power curves allow us to compare different simulations, different versions of ASCA. And these are the set of models that we wanted to compare. The first one does not consider in the factorization the individual factor, even if the simulation is incorporating it, of course. In the second one, we consider it as fixed wrongly because this data is simulated with a nested factor. Then the next three are correct, but we use different version of the statistic, the sum of squares, the wrong F ratio, and the correct F ratio. And finally, we have this for the ASCA Plus based on the general linear model, and for the LMPCA based on linear mixed models. So we start with a new example in which the effect is fixed to 0 for A, B, and AB, but we still have an increasing effect in CA. And what we see is that for all the different statistics that we have, for the sum of squares and for the F ratio, the effect in A, which is the color blue, is increased. So this is completely wrong because the effect is set to 0, and this is an inflation of the type 1 error in the group factor, which is exactly what we saw before in the real data set. So these two statistics are not a good selection. If we use the correct statistic, we don't see that inflation. But if we consider the individual factor as a cross factor, then we see some level of inflation in factor B. So the two most correct results are based on the correct model with the correct statistic based on GLM and LMM, sorry. But we can see that GLM is more powerful than the LMPCA version because it grows quicker, and at the same time the computational time is really much more it's much lower, 2 orders of magnitude than this, so we are comparing 22 seconds to 7 hours. So in principle this would be the adequate choice. Now if we select these two cases, which are essentially correct, for different cases of a positive simulation in which we have now an effect in all the terms of our design, and we simulated several cases with the power curves. A positive case that is completely normal distributed, one in which the residuals are non-normally distributed, one in which the individuals are non-normally distributed, and a case in which we simulate unbalanced numbers of individuals in the groups. And we can see that for all the situations, the behavior of the ASCA Plus model is quite good, quite similar, even in front of non-normality and unbalancedness. And also the time remains very low, computational time. While in the case of the linear mixed model, the time is very, very large. It's 7 hours, the time it takes for a single power curve to be computed. And also the power is slightly less because we see these curves grow slower than the ones at the top. So conclusions. It's very important to select the correct F ratio, and the correct F ratio depends very much on the experimental design, meaning that a good software package should solve for the correct F ratio when we input the data. It's very important that we have this ability computed into software. Then the nested coding is something that we also need to incorporate for this kind of design. So every time that we have a nested factor, it's very important to incorporate the correct nested case. And also I will say that the GLM solution based on ASCA Plus is much faster and even more statistically powerful than LIMPCA. So my option will be the use of ASCA Plus as a general solution for a software package. At least, or maybe it is worth mentioning that it will be nice to investigate alternative solutions for the linear mixed models in ASCA. And finally, according to our results, we have seen that the solution is robust in front of non-normal distributions and also unbalanced data. All these software solutions, including the power curves, the ASCA Plus, the nested and random solutions for the design, are incorporated into the software of the Meta Toolbox version 1.0. Thank you very much.